Hey everyone, we're on to Chapter 9, Lesson 2. We're going to talk about electric power and energy this morning. So here we've got a really simple circuit sketched out. We've got a single battery. Remember, the big bar is positive terminal, the little bar is the negative terminal. We've got an ammeter plugged in correctly, right in line with the wire. We've got a voltmeter plugged in correctly. It's piggybacking a resistor. It's checking how much energy before and after the resistor and displaying the difference. I just want to show you something kind of weird with units here. So let's say for this nice simple circuit that we've got, that we've hooked up a 12 volt battery. That would be like a car battery is 12 volts. What is that 12 volt battery actually doing? Well, 12 volts means that that battery is supplying 12 joules to every coulomb. And remember that a coulomb is just a bundle of lots and lots of electrons. So you've got a battery giving 12 joules to every one of those coulombs that's going to race around in the circuit. And let's say that we've got a current of 2.0 amps. So what does that mean? Well, 2 amps actually means 2.0 coulombs racing around past our ammeter every second. And we're going to have this circuit run for 4 seconds. So I just want to show you, this is a great equation to find electric power. I just call it PIV, P equals I times V. And I just want to play around with these red units a little bit, just so I can show you that the units are going to work out to be exactly what we want in the end. So in this equation, P equals I times V, we've got a current of 2.0 coulombs per second, multiplied by 12 joules per coulomb. So there's our current in amps and our voltage in volts, but we've actually changed it into what it really is. And if you look at what's going to happen with the units there, turns out the coulombs are going to cancel out. One's on the top, one's on the bottom. And we end up with this value that says 24 joules per second. Now, you might know this already from, did we talk about it in Chapter 6? We might have. Yeah, we did. What is power measured in? What? Exactly right. Power is measured in watts. And a watt actually means a joule per second. So just to show you how these units work out with this equation, P equals I times V, we end up with joules per second, which is 24 watts, which is exactly what we're looking for when we calculate power. The units should be in watts. Now, this equation here shows you that energy equals power times time. And I want to flip to your formula sheet just to show you where that is. It's actually not in the Chapter 9 section. It's not in the electric circuit section. You'll find your nice power calculation there. You'll find Ohm's law. You'll find that I equals Q divided by T, charge divided by time, that we chatted about last lesson. But we're actually looking right here. So back in the Chapter 6 stuff, we used this equation before. Power equals energy divided by time. I'm just rearranging that equation, multiplying both sides by T. Then it would say E equals P times T. So that's what we're using here in the notes today. Energy equals power times time. If you're burning through 24 joules per second, and you run this thing for 4 seconds, throw that in your calculator, you're going to get 96 J for joules worth of energy used in this electric circuit. So there's an equation using power, and then also changing that power into energy. We can do that simply by multiplying by time. Now, in your house, you on a day-to-day basis, you're going to chew through lots of energy. So it turns out that we don't talk about the individual number of joules that you use in your house on a day-to-day basis. The number would just be too big. So instead we have a new energy unit. This is how you pay for electricity and energy. It's something called the kilowatt hour. And sometimes people look and they go, but it's kilowatts, Mr. Heinrich, that's power. But it's kilowatts, which is power, multiplied by hours, which is time. And we just saw the equation, energy equals power times time. So it actually is a calculation of energy use. So a kilowatt hour is 1 kilowatt, 1,000 watts, working for 1 hour, which is 3,600 seconds. So it's like George Foreman with his magic 1,000 watt grill running for, you got your 1 hour parking sign. So it's 1,000 watts multiplied by 3,600 seconds. Turns out a kilowatt hour is equal to 3.6 million J for joules. Now, your house, I would guess on a day-to-day basis, probably goes through 30, 40 kilowatt hours, maybe something like that. So you can imagine 30 or 40 kilowatt hours would be 30 or 40 multiplied by 3.6 million. That's just how many joules you use in a day. And that number would be massive. And if you build people on the individual number of joules, let's try a calculation. Let's go on the low side here. Let's say that you use 25 kilowatt hours. Maybe it's a shoulder season. You're not running the AC too much or the heat or the lights. So it's 3.6 times 10 to the 6 multiplied by 25. You go through that many joules per day, and you typically pay your electricity bill per month. So you get a bill like that. That's how many J for joules you're going to burn through in a month running a household of 4 or 5 or 6 people. That's a huge number. And if you put that number on a bill for people, they would freak out. Right? They just look and go, oh my gosh, it's too much. We're never turning the lights on. Or sometimes students will say, well, why don't we just put it in scientific notation, Mr. Heinrich? And the answer is, if you put that number in scientific notation, probably 99% of the population would have no idea what the number is. But instead, we can say, hey, you burn through 25 kilowatt hours per day, and there were 30 days in the month. Oh, look at that. You use 750 kilowatt hours. And people look at the number 750 and they go, oh, I get it. I feel good about that number. It makes sense. It's not so big that it's scary. It's not in some confusing scientific notation. So that's, I think, the reason why we use this unit of kilowatt hours. It just makes it easier for simpler people out there. That 3.6 million joules probably cost you about 12 cents. For each one of those, and it might not seem like a lot, but you can ask your parents that electricity bills, they get pretty big. So it starts to add up quickly. So just to try a quick question here, how much would it cost then to run a 60 watt light bulb for 3 days? Maybe you go away for a long weekend, you forget to turn a light off in your bedroom, and when you come home after a 3-day vacation, evening time, you can see the lights on, and your parents start yelling at you for leaving that light on. It costs money! You gotta turn the lights off. Well, how much money did it cost? Easiest way to do this is to turn your power into watts and your time into hours, figure out how many kilowatt hours you've used, and then multiply by your cost, your 12 cents. So 60 watts divided by 1,000 would be 0.060 kilowatts. 3 days is equal to 72 hours. And so if you multiply those two things together, E equals P times T, 0.06 kilowatts times 72 hours, you have used, with that single light bulb running for 3 days straight, 4.32 kilowatt hours worth of energy. And we can now take that amount, multiply it by the 12 cents per kilowatt hour. Turns out it's about 52 cents. So here's what I don't want you to do, I guess. You might be looking at that going, well, that's 3 days straight. That hardly costs anything. 50 cents, what's the big deal? The next time your parents harp on you about leaving lights on, mine did all the time when I was growing up. All the time. Turn off the lights. Turn off the TV if you're not in the room. Well, I'm going back in 3 seconds. It doesn't matter. Turn the lights off. What I don't want you to do, I'm not giving you the license with this example, to the next time your parents harp on you about turning off lights or saving electricity, to do a quick calculation on your cell phone and figure out that it cost 2.4 cents to leave that light on for a few minutes while you left the room, and then you're digging in the pocket to throw change at your parents. Like, here's a dime! Keep the change, you cheapskates! That is not what we're going to do with our folks when they get on us about leaving the lights on. They probably cook for you, they probably clean for you, they probably do lots of nice stuff for you. So let's be nice. We're going to grit our teeth. We're going to say, yes, Mom, yes, Dad. I will try to remember to turn the lights off. Now, I want to show you a couple more equations to find power. We've already seen P equals I times V. You'll notice in this circuit, we've got our battery connected to a resistor. We've got ourselves a voltmeter, but it looks like we're missing an ammeter. Maybe somebody hooked it up incorrectly previously and let all the smoke out, lit it on fire. So what are we going to do? P equals I times V doesn't work because we don't know what the current is. We don't have our ammeter. Now, we can do something a little bit clever here, though. We do know Ohm's law from last lesson. Ohm's law said that current is equal to voltage divided by resistance. So what we're going to do is practice some of those awesome math skills you've learned over the years. We're going to take this voltage over resistance. What if we simply did a little substitution? What if we just plug that in place of current? So that would look like that. P equals V squared over R times V. And if you multiply the two V's, we can clean this up. We get P equals V squared over R. It's another great equation you can use to find power. And it's great if you know how much voltage you're spending at that resistor. So if you ever have a circuit and you don't know the current, you don't have to find it. You could if you wanted to using Ohm's law and then use P equals I times V. Or you can simply go with P equals V squared over R. Works great. What about this scenario? What about if you have an ammeter? So maybe you went and found one, you've got your resistor, but your nice fancy digital voltmeter, you've loaned it to a friend, you don't have it for a moment. So you can't hook it over top of that resistor to see how much voltage or energy it's using. P equals I times V, that's not going to work because we don't know what the voltage is. But Ohm's law says V equals I times R. I've just rearranged Ohm's law a little bit there. And we can do one of those cool little math substitutions where we say, hey, why don't we just take that and plug it in place of V? Your equation ends up looking like this. P equals I times R. And if you clean that up, the two I's multiplied together, you get P equals I squared times R. And that works great if you know how much current's going through the resistor and you don't have your voltmeter. So it turns out there's actually three equations you can use for power. Let me quickly show you that on the formula sheet. Scroll up to the chapter 9 section. You'll notice we've got all three of them sort of stacked together right here. Sometimes students get confused because they go, what the heck, how am I supposed to use that equation? There's actually like four of them and three equal signs. Well, the answer is if you want to find power, you just pick one of the three versions. I times V, I squared over R, or V squared over R. And it just totally depends on what we've given you in the question. All right, let's try out one easy example here. We are asked to find the power from a 2.4 kilo ohm. Keep in mind that's 2.4 times 10 to the 3, 2,400 ohms. That's a big resistor, and it's connected to a 12-volt battery, up to your car battery. So think about Ohm's law. Last lesson we talked about sort of having a more intimate knowledge of Ohm's law. 12 volts, not a huge battery. 2,400 ohms, that's a big resistor. What happens when you have big resistors? Well, you have small currents, right? So keep that in mind. In this case, we're looking for power. P equals I times V. We talked about the current being small. We don't actually know what it is. And it turns out we don't really actually even need it. You could go and solve for that small current and then use P equals I times V. But maybe the best bet is just going to be to use one of the other power formulas. What about P equals V squared over R? We know what the battery is. We know the size of the resistor. You go and you run the numbers. I'll do it for you here to save you some time. You get 0.0600 watts, which, doing a little unit conversion, we talked about how electricians like to do that, they would call that a power of 60 milliwatts. So there's a nice, easy example where we didn't use P equals I times V. We went and used one of the other equations for power just because we didn't have the current. All right, so let's try another example. This one's a little bit trickier. So I'll give you that heads up. We have to think about things a little bit. We're going to find the power if we take a 9-volt battery, hook it up to some circuit, and it gives us a current of 0.50 amps. So part A, find the power. 9-volt battery, it's a kind out of your smoke detector, and it's giving us half an amp. Probably easiest just to go P equals I times V. So your current of half an amp multiplied by your voltage of 9 volts gives you 4.5 watts as power. PIV, P-I-V. Done. There's part A, very easy. Here's part B. Let's find the power if we switch up the battery. So we're going to yank out that 9-volt battery and we're going to plug a bigger one in there, a 12-volt battery. And you look and you go, okay, cool. 12-volt battery, 0.50 amps, P equals I times V, 6 watts. Done. But that's actually incorrect. You have to think about Ohm's law here. Anytime we switch batteries, that's key in this question. When you see something switched in a circuit, whether it's a resistor or a battery, you have to be really, really cautious as to what impact that has on the current. We have to remember that when you bump up the voltage in a battery, as discussed in the last lesson, that is going to give an increase in the current. So here we have to have that sort of more intimate, that deeper understanding of Ohm's law. So the voltage is increased, so the current's going to increase. That means you can't use this 0.50 amps anymore. Now you might be looking and going, well, what the heck do we do then? How do we get the new current? And the answer is you have to figure out what the resistance was. Because remember, if we switch the battery, that has no impact on the resistor itself. So what I would do in this question is I would say, ooh, careful, careful, we're switching the battery. That means we have to go and we have to find some more information. So what I would do is use I equals V times R, I equals V divided by R, Ohm's law. Let's find the resistance using the original information from part A. So we had a 9-volt battery giving us 0.50 amps. If we plug those values in for V and for I, what does R come out at? And if you rearrange that equation, it turns out that the resistor was worth 18 watts. Or sorry, that should be ohms. Let's take that out of there. Resistor is 18 ohms. And that's going to stay the same always. The only way you're going to change that resistor is if you physically take it out and you put another one back in there. So we've got this resistor worth 18 ohms. Now, some of you might be looking and going, well, we just talked about that current increasing because the voltage increased, but do we even need to use the current? Do we even need to go find what that increased current is? Because what's cool is if you think about part B, we know the voltage is 12 volts. We just found the resistance. Is there a way we can find power just with those two things? And the answer is yeah, you definitely can. You can use P equals V squared over R. So it turns out we had to think about the current changing, but you don't even have to go find that new current, which is kind of cool. We can simply use this. We've bumped it up to 12 volts, so 12 squared over that 18 ohms. Let's see what we get. Fire up the calculator here. 12 squared over 18. There it is, 8. So it's actually 8.0 watts is that power. Now the other option, in case you wanted to do this, you could have gone and found what that new larger current was. I equals V over R. We bumped it up to, what have we got, a 12 volt battery over 18 ohms. So we had half an amp in that first part of the question, but now we're up to 0.667 A for amps. And then you could have taken that and you could have plugged it into maybe something like P equals I times V. So this works too, it just takes a little bit longer. 0.667 times 12. There you go. Get the same answer, 8 watts. So the takeaway from this question is, and I'm giving you a heads up that you're going to see these in the homework, when you switch something, when you switch the battery, you make it bigger or smaller. So here we change the voltage. If you change the resistor, be very, very cautious and think about what other changes that is going to make in your circuit. Specifically, how is that going to change up your current? So have that intimate, deeper understanding of Ohm's law. Always have that running in the back of your brain. You should be just fine. Check out the Chapter 9 outline for some more textbook questions based on this information. If you have questions about the lesson or questions about the homework questions themselves, please fire me an email or join me on Zoom. It would be great to see you and chat with you and go over some physics. Take care, everyone.